Welcome back, everybody. In this video, I'm going to be going over a solid strategy for dimensioning the bearing housing on a gearbox. Let's look at the different ways that having poorly positioned bearing boards can impact the way that gears are meshing. So to start, we'll look at what a properly aligned set of gears looks like. And then the first type of misalignment that we can have is axial misalignment. And you can see that this doesn't really depend too much on the actual bearing bore position themselves. We can also have radial misalignment, yaw misalignment, and if we look at it from the side, pitch misalignment. Now let's watch how the bearing bores need to move to create these types of misalignment. And again, we can't see any movement in the bearing bore to create axial misalignment, but we can see movements in the bearing bore positionally to create radial misalignment, yaw misalignment, and pitch misalignment. So many engineers are tempted to take those bearing bores and apply a positional tolerance relative to some dowels that are on the bearing housing. And this is good, except that you may have noticed that these misalignments are created due to the positional variation between the bearing bores, and not necessarily the bearing bores relative to the rest of the case. So you might have an instance, like I have in the past, where you can actually accommodate quite a bit of movement relative to the dowels on the bearing housing, but the locations of the bearing bores relative to one another is actually very important. So how would we create a tolerancing scheme to accommodate this? So we're going to look at a few different cases, the first of which is the simplest, which is where the bearing bores are the same size. So to start, this probably won't be very controversial. The big flat face that's probably going to seal in all the oil in the gearbox is going to be our datum feature A, and it's going to have some flatness applied to it based off of the gasketing material that's going to be used. The secondary datum feature for the part is going to be most likely some pattern of dowels, and everything is going to be located relative to these two datum features. The bearing bores, in this case, like I said earlier, they might be able to move around quite a bit relative to the part itself, but we want them very tightly located to each other. So this would be the perfect opportunity to use a composite positional tolerance zone. So in this case, the upper segment would be related to datum feature A and B and would be fairly loose to allow those bearing bores to kind of move around on the part. But then the lower segment would be a little bit tighter, and this would be based off of the, some calculations that we do to determine what kind of misalignment on the gears is acceptable. And this would hold those bearing bores much more tightly located relative to one another. And in this case, they would be able to rotate relative to datum feature B. The second case we might see is where the bearing bores are actually different sizes. So again, we have the same primary datum, the same secondary datum, but now looking at the bearing bores themselves, things are going to change a little bit. We're going to pick one of the bearing bores, and it's a little bit arbitrary. In this case, we're going to pick the larger bearing bore and say that this is datum feature C. So we will locate this bearing bore with that looser tolerance relative to datum feature A and B. And then instead of having a composite positional tolerance zone, because these are different sizes, we'll actually relate the smaller bearing bore, in this case the 80 millimeter bearing bore, to datum feature C. So we will have a looser tolerance zone relative to AB, and then a tighter tolerance zone relative to AC. And this achieves a very similar thing to what we see with a composite positional tolerance zone. It allows both those bores to move around up, down, left, right relative to datum feature B, but it keeps those bearing bores nicely located relative to one another based off of the math that we've done to determine how much variation we can handle. And the beauty of this approach is that with the cascading datums, you give the maximum amount of flexibility to the manufacturer of this part. Whereas with a composite positional tolerance zone, you've locked in that pattern quite tightly relative to one another. And it works well if you're only looking at 2 bores, but if you're looking at 5 bores, well, you don't really care about the relation of 2 bearing housing bores if they don't have shafts that are interfacing with one another. So with the cascading datums, let's look at this example with 5 bores that are all different sizes. if the shaft that is installed in datum feature C interfaces with the shaft that's installed in datum feature D, we'll have datum feature D reference datum feature C. And likewise, if the shaft that's installed in datum feature D interfaces with the shaft that's installed in datum feature E, we'll make a direct reference between those two. But you don't care about the location so much of datum feature C relative to datum feature E. So why would you lock those in together with a composite positional tolerance zone when you can have them only look at the shafts that they are going to be directly interfacing with? So next time you are designing a bearing housing or a gearbox, consider using this cascading datum feature scheme. And if you need help with the tolerances, feel free to reach out to Access GD&T Services. We have worked on this type of equipment before, and hopefully this was helpful. Have a good one.